Welcome to the podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to talk about projectiles.
Guns.
No.
No.
Well, maybe. Projectiles, but first we're going to talk about the acceleration due to gravity, which we signify with a lowercase g. And if there's anything you learned this year, I hope, or anything that you choose to memorize, this is the one thing that's actually worth knowing, because you're going to use the acceleration due to gravity repeatedly. Negative 9.81 meters per second squared.
Negative because it's toward the Earth.
Correct.
And meters per second squared tells me that it's an acceleration, not a velocity.
That is correct. That would be the units that would give us that. All objects fall at this rate. So in my class, we've done this silly experiment where it's actually not silly. It's actually pretty ingenious. But we take one piece of paper and crumple it up, and then we take two pieces of paper and crumple it up. We drop them from the same height, and lo and behold, what happens? They hit the ground at
the same
time. Yeah. And that's because weight doesn't matter. Gravity can't see the weight of an object. It just acts on all objects exactly the same.
Well, and isn't that the experiment that they actually did on the moon, a feather and a hammer?
Correct.
And in the vacuum of space, they both hit the moon at the same time.
Due to a lack of air resistance.
Right.
I had to crumple up the papers in the classroom, obviously, to make it work. So the first thing I'd like to talk about is just throwing a ball straight up into the air. So I've got this ball, and I throw it up into the air, and it sort of takes this path. Now we want to assume that it's straight up and straight down. I'm drawing it in 2 dimensions just so that we can see it.
Right.
Okay. Now, as I throw, let's say I throw the ball up into the air with an initial velocity of 40 meters per second.
Okay.
On the way up, what can you tell me about the speed of the object?
It's going to slow down.
And it's going to slow down according to the
Gravity.
acceleration due to gravity,
Right.
which is negative 9.81 meters per second squared, which is really, really close, just for our purposes, close to
10.
negative 10. So in the next second, so if this is time is 0 seconds, at second 1,
It should be about 30 meters per second.
because we have, it's on its way up, we have a positive velocity over here on the left
And a negative acceleration.
with a negative acceleration. So it is in fact slowing down. Seems like that question came up on the test a few times.
I explained that to a couple of students more than once.
Right.
That gravity is constant. On the way up, it's pushing down, and on the way down, it's pushing down.
Yeah. In the next moment in time, at second number 2, is gravity still acting on it?
Absolutely.
In exactly the same way?
Exactly.
So it should be going up, but at a much slower rate of
20.
20 meters per second. Still a positive velocity with a negative acceleration. At second number 3,
10.
it slowed down even more to 10 meters per second.
Right.
And then at the very top of the path, at t is 4 seconds,
Right. It's 0.
it's 0. So for this one moment in time,
It's basically the
It's-
velocity has stopped.
it stopped.
And I had students say that the acceleration stopped. Well, we know that doesn't happen. You don't throw stuff up in the air and it hits the top and stops in midair. That doesn't happen.
Right.
So acceleration is still pushing down.
So we're kind of filling this chart in, and we start to see some trends here. On the way down in the very next second, so t is 5 seconds, gravity still got a hold of it, right?
Correct.
It's on its way down, right?
Correct.
So its new velocity from 0 becomes,
10 meters per second, but in the opposite direction.
10 meters per second down. Right, so a negative velocity with a negative acceleration means it's going to start speeding up.
Correct.
So now this is 20 meters per second down.
Correct.
At time is 6 seconds. And this is 30 meters per second down at 7 seconds. And if we catch it where it starts, that's time is 8 seconds, so 40 meters per second down. It was very purposeful that we chose numbers like 10 and 40 and so on. It makes life easier to analyze this. So this, we did some DT and VT and things like that before. let's get a little more specific. Let's say yt, the vertical position, and the vertical velocity versus time, and the vertical acceleration versus time. So that y that we see in math class does in fact work. It does in fact go up and come back down. Hey, we've seen that graph before. And it does in fact start with a positive velocity, become 0, and eventually negative velocity. We've seen that graph before too. And hey, it is constantly negatively accelerating. We've seen that graph before too.
Correct.
So the tossed ball is what this is equal to the inclined ramp with cart.
Right, so this would be the same motion if we pushed it up the ramp and it came back down the ramp.
Exactly the same. So it starts to lead us into this whole world of projectiles and what all of this means. So we're going to show you a short video clip here so that you can see gravity in action. All right? So let's go ahead and take a look at that now. So that was interesting. We had this little physics device, and all we showed you was this little ball, and the ball started falling. Is that
Correct.
true? So at the first moment in time, what is its speed?
0.
Its speed is 0 meters per second, and what is its acceleration?
Acceleration due to gravity is
Right.
always the same,
So
negative 9.8.
1 meters per second squared.
That are we gonna round it to 10 again here?
Let's get a little more specific.
Okay.
It's going to make, well, it's not going to matter. And so in the first second, you're going to determine that it doesn't fall very far. And you can actually break this down. I guess when we start talking about this, it doesn't really fall for more than a second. Actually, it doesn't fall for a second because gravity is so big. But in the first second, it would acquire a new speed of negative 10 meters per second. I'm sorry, that's wrong, isn't it? The gravity I'm sorry, because of gravity, it won't be 10. That was a nice assumption that we made before. It'd be negative 9.81. And gravity is still causing the acceleration. In the second you would notice that it's continuing to gain speed, so it'd be negative 19.62 meters per second. And the acceleration is still due to gravity, which is constant. And in the third second, it would fall even farther. And so negative 20 something, almost negative 30. I had to cheat. And so what you notice is that when gravity acts on this thing, it falls farther and farther in each moment in time, and it gets faster and faster.
Well, we know that if you jump out of a plane, you speed up.
Right. Yeah. I won't be jumping out of any airplanes.
Me neither.
But yeah. So let's watch the second video. Let's instead of watching the ball drop, let's shoot it this time. Except this time, I'm going to help you out. We have a launch angle is equal to 0 degrees. So I want you to think about that, and let's go ahead and watch that video. So that was a little different than the first one, wasn't it?
Right, because we're shooting it basically horizontally.
So we gave it some initial velocity to the right, but the flight of the ball did something like this. And so I got some questions, Mr. Sadler. When we're looking at this, in the first second, is gravity acting on it?
Absolutely.
And in the second?
Absolutely.
And in the third?
Yes.
So if gravity is still acting on it, what's going on here? So the A is still equal to G. The V at t is 1 second must be really close to what?
10, 9.81.
Yeah, negative 10 or negative 9.81. And in the second, is gravity still the acceleration? Yeah, so the velocity must be around
10, or I'm sorry, around 20 now.
negative 20. Yeah, we've added 10 more to it. And at time is 3.
very close to 30.
Yeah, but because of gravity still acting exactly the same, that's really fascinating stuff. But notice, even though it's falling, going farther and farther, moving faster and faster on the way down, it's still going to the right.
Correct.
What can you tell me about these horizontal distances in each second? They're about,
The same.
yeah. Why do you think that is?
Because it was launched at some speed, and that's the only force that was on it, and we're not speeding up or slowing down.
Right, there's no
So the horizontal has to be the same.
horizontal force left to right to speed it up or slow it down. And as a result of that, horizontally it's traveling at a constant speed.
Correct.
It's really interesting. So let's draw the graphs on this. Let's see, let's go y versus t. And I suppose we'll talk about why I'm drawing it like that.
Because it's falling down.
And ay versus t. Let's go with blue on that. So on the way down, it starts with no speed, right?
Correct.
It gathers some speed and it finishes fast on the
Right.
way down. So something like that.
Dropping and speeding up.
Oh, something like that.
Acceleration, right.
And something like
Correct.
that. That's g, by the way. That value that is sticking out over here is negative 9.81 meters per second squared.
Because it's falling due to gravity.
We've seen these graphs. If we're calling where it starts 0 and everything below it is negative, this works.
Right.
There's other correct ways to draw the graph. Then what about the x? This is where life gets interesting.
Well, we just said that the x is, the y is speeding up, but the x is constant.
Yeah, so wait a minute. So the speed is constant in the x direction?
The speed is constant. Yes.
Yeah. So there's no horizontal acceleration.
Correct.
So-
there's only vertical acceleration. It's speeding up going down, but is going the same speed. Like if you shoot a bullet from a gun, it doesn't speed up or slow down.
After it's left the gun.
Correct.
So the horizontal acceleration is zero.
Zero.
The horizontal velocity is constant,
Correct.
which means the distance it covers in each moment in time.
Nice straight line.
Yeah. Notice how different those are. On the test, weren't you frustrated when kids told you that it had both constant velocity and constant acceleration?
Constant acceleration cannot possibly be constant velocity.
It's impossible. We show it right here. Hey, this is constant acceleration, curvy distance time. This is constant velocity, linear distance time.
Notice how the velocity is straight. The velocity is the same.
That's interesting.
Yeah.
So the last thing we're going to show you is we're going to show you the drop and the shot at the same time. And what we'd like you to, we have a real quick question. Drop and shot. Let's see. Who thinks that the drop hits first? Raise your hands. We can see you. Who thinks the shot hits first? Raise your hands. We can see you. Who thinks it's the same? Raise your hands. We can see you. Let's take a look at that.
3, 2, 1. 3, 2, 1.
Welcome back. Well, that was a broken experiment, wasn't it? What happened?
Absolutely. It's both hit at the same time. Because whether it's shot or dropped, the only force acting on it is in the y is gravity.
Right. Gravity doesn't know the difference. Right? When I say it doesn't know the difference, it doesn't know the difference between falling or falling and moving to the right.
Correct.
Okay? And that goes right back to the what do you see picture where the guy's trying to make the observation at the same time. We're going to do this demonstration in class, and what I want you to do in class is I want you to trust your ears. Close your eyes and trust your ears, and I guarantee you, you're going to think only one object hit the ground.
Right. And they do this, Mythbusters, they do this with a bullet dropped versus bullet shot.
That was a whole hour, and they took a lot of time to figure out the initial velocity of the bullet, and it was a huge problem setting the experiment up. But in my opinion, was one of the few things they actually got right.
Right.
They usually leave something out, but they planned for everything in that episode. So that's a lot, but we just covered projectiles and zero degree launch angles. So signing off, this is Mr. White.
And Mr. Sadler.